Okay.
सुनो ना, यही वाला जो लिंक है ना यूट्यूब पे, ये जीमीट के चैट में डाल दो ना इसको, तो अपना देखते रहे। Yes, your slides are visible.
Okay, great.
And in the chat window, we have sent the YouTube link where you can see your live streaming whenever you want. Okay, so we can start with the session. So I welcome you all to this session on by Luceda Photonics. So the Luceda Photonics is now going to show us how we can use their tools for PIC design. The session will be given by Toons Snowert, and he is an application engineer at Luceda Photonics. So welcome to the session, and let's get started too. And if you have any queries, you can ask during the session. Thank you.
Oh, okay.
We can start.
Thank you very much. Yes, thank you for inviting us to this course. So the session will be about getting started with PIC design. And I've created a schedule for this. So first I will talk 15 minutes about Luceda and our photonics design platform. And then we will start with an online training in which we go to the principles of circuit layout and schematic design. Then I also talk about component layout and simulation, and eventually circuit simulation. And after we've done this training part, I will show you an application example that you can find on Luceda Academy, which is our online platform, in which we explain how we create an existing chip, which is a quantum key distribution receiver, and how we fully simulate it. And in the end, there will also be time for questions. So I'll first start with an introduction about Luceda. So Luceda Photonics was born in 2014 from the Belgian photonics ecosystem. And our vision is to help photonic IC designers enjoy the same first-time right experience as electronic IC designers. And we do that by helping you set up a flexible and efficient big design flow. We have a global presence all over the world. So our main office is in Belgium.
Tun, sorry for the interruption. I think you have switched your slide, but right now we cannot see the next slide.
Okay. Is there...
we are only seeing the first slide.
Really? And is it because of lag? It's not coming, no. Did you see the schedule slide? Can you still hear me? Can anyone still hear me?
Yes, we can hear you, but we cannot see your slides.
Okay.
Can you just do entire screen and then switch over to...
Yes. So now I am sharing my screen. Can you see my slides now or not?
Not yet.
There's a bit of a delay. Did you see only this slide, or did you only the first slide, or did you see other slides as well? I see in the... Can you still hear me now? I can't hear anyone anymore. So maybe I'll try again sharing my screen. Can you see my slides now? Can anyone hear me? If you want, you can put it in the chat if you can hear me. I'm sorry, was there?
Sorry, we were disconnected. So we have rejoined. Hope our voice is reachable to you.
Okay, now I can hear you clearly.
Yeah. So can you once again share your screen?
Of course. So now you're seeing my slides, is that correct? I can't. I'm having trouble with hearing you.
We can only see your first screen.
Can you maybe put in the chat That will be easier.
We can not see your screen, please.
Okay.
You go. Now it is visible. The first page.
Okay, now it's visible. Okay.
Yes.
And so now I'll start from this slide. Can you see my second slide now, or?
No, it is in non-presentation mode.
Okay.
You do one thing. You share your entire screen.
Okay. I'll try again sharing my entire screen. Okay, so now I'm sharing my entire screen. Can you see the slide now? And can you see me changing from slide to slide?
No. Right now, you are not sharing anything. Yes, now we can see.
Okay, there's probably quite a delay going on.
Yes, now you go to presentation mode.
Are you seeing the schedule slides now?
I am seeing entire screen. Yes, now I see.
The schedule slides or
yes.
the?
Now I can see your first slide. Yeah. Yes.
The one.
Yes. Now the schedule we can see. Yeah.
Okay. Okay. There's quite a bit of lag probably. So if the slides don't follow my explanation, please tell me.
Yes. Yes. Sure.
Okay. So I was talking about Luceda Photonics. So our mission is to help photonic IC designers enjoy the same first-time right experience as electronic IC designers. And we want to do that by introducing the Luceda Photonics design platform. And this platform introduces a code-driven flow that helps all the users through component design, circuit design, design validation, until your eventual tape-out. We do this by, with this approach, it has a few advantages. First of all, we can reduce the design errors because we are working from one central platform and where we design and simulate parametric components and circuits. Then everything is scripted in Python. And we have a wide range, variety of PDKs for different foundries and different material platforms. And by being able to document and maintain and reuse your IP with our code-based approach, we are able to improve your time to the market. So here you can see all our design kits. So we have for different material platforms, silicon nitride, indium phosphide, and also some assembly and testing PDKs. Then our core product is Luceda Ipkiss, which presents a code-driven flow that helps you through component design, circuit design, design validation. We also have simulation solvers. Our components can be simulated with our own solver, which is Camphor, or you can also use links with some of our design partners, like Lumerical, Simulia, Tidy3D, and use these links to simulate components that are created with our software. And in the end, everything can also be exported to a GDS file. So the starting point of our design flow is component design. And we do this in one standard language, which is Python. And when we create components, we create parametric components that have a layout view and a simulation view. And afterwards, they can be virtually fabricated, and you can simulate them with either our own simulator or with third-party tool simulators, such as Tidy3D, Lumerical, and CST. Then the next step is circuit design, in which we implement a code-driven circuit design. And we have lots of smart optical and electrical routing techniques, in which we can also avoid certain obstacles, create bundles of connections, and so on. When we create circuits, we also do it. We also create parametric circuits, and we can simulate it with a Caffe or simulation engine, and we can do frequency and time domain simulations. Then a different way to create a circuit is by using our schematic capture, which is a IPGIS canvas, in which we create a schematic of our circuit that can be directly converted into our codes. Then afterwards, we can validate our design by checking the connectivity, by doing netlist extraction or post-layout simulations. And in the end, we can also help you with tape-outs. We can help you detect your overlapping layers, fixing your snapping errors, and patching some acute angles. Is everything okay with the slides so far? Can you, can you follow?
Yes.
Okay. Thank you. So we have a lot of design kits, and they are all scripted in Python as well. And all these PDKs have lots of components that are predefined and that also have models. We can also use these components in Canvas, and we can also export them to open access and new PDK standards. So at Luceda, we offer a big amount of training and support so that you are able to maximize your design potential. To every new customer, we give onboarding training. We have a lot of training material and documentation. Luceda Academy is our online platform where you can look for tutorials and guides. We have a customer support portal that is very active. And we also offer a lot of application support and have a vast offer of training events. Luceda is part of a big ecosystem. We have software partners, design service partners, ecosystem partners. We also participate in a few EU projects. And if you are interested, or if you know people who are interested, we are always looking for new people to join our team. You can check out our career page or send your CV to hr@lucedaphotonics.com. On the site, you can also have a look at some of the people that work at Luceda, and you can always connect with us on LinkedIn if you have any questions. Then I told you about Luceda Academy, which is our platform where we have lots of guides. So if you want, you can always have a look at the lucedaacademy.com. Like, for example, I'm showing you here Luceda Academy. We have lots of tutorials to help you with getting started. And also, if you're already a bit more experienced user, we also have more guides. And there we have a vast amount of application examples as well that you can have a look. So that was the introduction. Now we can get started with the training. So these are a few guidelines of the training. It is an interactive training, so you can always ask questions in the chat or by asking here in the meeting. You can, well, you probably all joining on the same link, so that's not really relevant, but the training is a presentation, and then I will also show you a demonstration of IPKIS Canvas. And I will share the, yes, is there a question? By asking here on the meeting, you can, well, you probably all joining on the same link, so that's not really relevant, but the training is a presentation, and then I can hear my voice. I think there's some lag going on. Can anybody still hear me?
No question. Yeah, you can continue.
Okay. So the application example that I will discuss at the end of this session is a quantum key distribution receiver. And in this receiver, a quantum key is decoded from laser pulses. And it's created in a silicon nitride platform. And it is compatible with certain protocols, the BB84, the COW, and the dual phase shift protocol is a protocol that we will implement for this example. We will use our SciFab PDK components to create a layout of this circuit, and then we can extract it to GDS, export it to GDS, and then it will look like this in a GDS file. Everything in the circuit is created with IPKIS, so from the optical I/O all the way to the electrical routing with the bond pads. And then we are also able to simulate it by using our CAFE engine, which is our simulator engine, in which we create a test bench where we can do a time domain simulation. So we input some pulses, laser pulse, where the quantum key is encoded in the phase difference between the pulses. And then by going through the circuit, this output, here the pulses are recombined and the key is decoded by these two photodetectors. But before we get into the working principle of this chip, we'll start with something simpler. We'll create a circuit layout of a splitter tree with 2 levels. And so here we connect 3 connected splitters with grating couplers at each input and outputs. And for that, we will use components from a process design kit. And inside a process design kit, you can find all the information that you need to be able to successfully tape out to a specific foundry. So that information is, for example, predefined components used by the foundry, some of the technology layers, also some of the properties of the bands, for example. When we create such a circuit, we always use I3 circuits where we define the instances first, then we place them on a certain position at the grid and we connect them with each other. And in the end, we choose the ports that we want to export to the outer world. So the first step is defining the instances dictionary. And here we go into the method default instances and we take out an MMI out of our PDK that we've defined. And to create our splitter, we need 3 of these MMIs. So we create 3 references of these MMIs and we give them all a name. Then the next step is the specs, where we, inside the specs list, we place the MMIs. And for that we use placement methods. So here we place MMI 0 at location 00. And so on, MMI 1 at location 100 minus 25. Once we've placed our MMIs at certain locations, we want to connect them with each other. And for that, we define connectors. And in our case, we will use the connect band connector. We select the ports we want to connect with each other, and then automatically waveguides will be generated between these ports. Once we have a connected circuit, we can choose the ports that we want to expose, which are the unconnected ports in this case of our circuits, and we will give them a name. So here we use the inputs and the 4 outputs of our splitter tree. Then all there's left to do is create a main program in which we create a full splitter tree and visualize the layouts. And eventually we can also write this to GDS. So let's go into a bit more detail about placements. We can create a place. So I told you about the placement functions. I told you about I3 place. Then there's also join, align, and flip. So if we place our MMI at a certain location, there are different ways to do that. We can also select a certain port of our MMI and place it at a certain coordinate. Then we can also place our coordinates relative towards other coordinates. And for that, we use the relative to parameter here, in which we select the port we want to place our component relative to. And then we select the distance in the X direction and the Y direction, which we want them placed apart. And we can also rotate our components by changing the angle here. This is all done inside the placement methods. Then we can place at certain coordinates, at certain angles, and so on. A different function than I3 place is I3 join. And when we use I3 join, we actually connect 2 ports directly with each other. And for that, we select the ports we want to connect and use I3 join. Then we can also flip our MMI in a horizontal way and in a vertical way. This function aligns components. You can choose 2 components or 2 ports that you want to align with each other, either the X coordinates or the Y coordinates, using align horizontal or align vertical. So that was about placement. Now I can also go a bit deeper in the connectors we use. So one type of connector that connects ports with each other is the connect Manhattan. And this connector creates waveguides that only go to a horizontal or vertical coordinates. And there are 90-degree bends between these waveguides. You can select the bend radius of this bend and also the rounding algorithm of this bend. So here you can see the bend radius is 6. So that was connect Manhattan. Then we also have connect bend. And connect bend connects 2 points through as simple as possible bend. So this is this connection. Here we create an S-bend between these 2 ports by using connect bend. with connect bend, we can select a rounding algorithm that describes how the bend rounds. Then you can create different types of bends. We can create U-bends. And since we can angle all our components, we can deal with any orientation of the ports. So that was about connectors. Then I've told you that in IPKIS, we like to create parametric circuits because then we can create photonic circuits in a very flexible way. And what I'm showing here is the code on how it looks like to create a parametric splitter tree. And for that, we define our parameters, which are splitters, and the grating couplers, and the spacing between our components in the x direction and in the y direction. So then we have a default method of our splitter over here, in which we decide which splitter we will use at default, which is an MMI that we take out from our PDK. And we do the same thing for a grating coupler, which is this grating coupler component also out of our PDK. And then we will go into the specs here, and we can use these parameters that we defined to create a parametric circuit. And this means that now we can select any spacing we want, and it will create a completely different circuit. I will show you in PyCharm. So now I will go out of the slides and go into Luceda Academy on PyCharm. Can anybody see PyCharm now? Maybe I'll have a look in the chat. Okay. So I will go into PyCharm.
Yes, sir.
Okay. So when you open Luceda Control Center and you go into PyCharm, this is how your project looks like. You have a training folder, and then you can go into Getting Started. You can go in. I will go into PyCharm. Yes, sir. I could hear my voice again, but that's... So, when you open Luceda Control Center, okay. I could hear myself. Is everything okay with the connection? I think I will continue. Please, if you can't hear me, you can always put it in the chat, then I know. So when I go to PyCharm.
Yes, sir. Please continue.
Yes. When I go into PyCharm, you can see here the Getting Started. We have circuit layouts, and then we can have a look at a few of our examples. And the first one here is a splitter tree circuit, in which we've created instances, and we've created specs, and we create our main program. So now if I just right click and run this, then I can see my splitter tree being visualized. And if you go here in 4 parameters, then you can see a parametric circuit of our splitter tree. And here we have the same way we always create a circuit, and that is we start by importing the SciFab PDK. Then we import the functionality of IPKIS. And then we can start by creating our class. We have our parameters here, our default methods for our parameters, then the instances, and the specs. And then also the connectors we add to the specs. And we have the expose ports. And here in the main program, we can create a splitter tree where we choose the spacing between the components. So if I run this now, a splitter tree will be created with 100 in the y direction between the components and a 50 in the x direction distance. And after that, it will also create a different circuit. Now we're at this part of the code where we select a different type of splitter. And we can use that inside our splitter parameter. So also the components we can change inside our circuit. So here we choose, instead of an MMI, we take a Y branch, and then we get this circuit, in which now we can see a Y branch as splitting components everywhere. Okay, then I'm also going to show you how to go to Canvas. Control center. So this is a Luceda control center. And then you press Canvas. And you create a new project. You can also give it the name splitter tree. Then we can select a path on which we will save this, which can be done here. And then we add the IC.lib file of our PDK. And inside this IC.lib file, so for that you need to go to your users folder, then to Luceda, Luceda Academy, and the version you have. And then you go to PDK sources, SciFab. And this IC.lib file is the one we select. And then we can create our project. Now in Canvas, we have our library of SciFab. And inside this library, you can see all the predefined components of Silicon Fab, which is our PDK that we use for demonstrational purposes. And what we can do is we can take these components and just drag and drop them. So here I'm drag and dropping some grating couplers. I can nicely align them with each other. I can mirror them. And then I can drag other components like the MMIs. Over here. So now the next thing we can do is we can just connect them by selecting the ports we want to connect with each other. And the next thing we can do is we can create exposed ports. And then we do that by creating external terms. Then we can connect them with the ports we want to expose. So here, for every grating coupler, every output of the splitter tree, we can create such a exposed port. In every component, we can also have a look at their properties. I see there's somebody wants to I've added yes, I've added someone to this meeting. We'll go back to Canvas. So this is a splitter tree I've created. I was talking about that you can go and have a look at the properties of each component, and then you can see a name which you can choose, like this is the grating coupler, outputs 1. And we can also give it a specific position. If this was a parametric component with parameters, you could also give the parameter a different value and so on. Same you can do for the exposed ports. We can give them names, output 1, output 2, and so on. So we've created the schematic of our circuit. And starting with a schematic is an easy way if you still are developing your circuits and you want to ask your supervisor or your colleagues what do they think of the circuits. It's easy to interchange your circuit fast. And when you are finished with what you want to create, you can create a code template of your circuit. And this code template creates an I3 circuit of the schematic that you've made in Canvas. So we have the same structure. We have the instances, we have the specs and the exposed ports, and also the main program. So all we need to do actually is we need to copy this, and we can go into PyCharm and create a new file here, new Python file, splitter tree. We'll create it here. And paste. And now we can directly run it. And then we will see the splitter tree that we've created in Canvas. But there's something strange going on. We can see that the waveguides are not waveguides, but they are these purple lines. And that is because in this template, we used Connect Logical, which only creates logical connections between your components. What we want to do is we want to create waveguides, so we can change this to the Connect Bend or the Connect Manhattan. If we run this now, we can see that now between the components, we have actual physical waveguides. So once you've created a schematic and you've taken out this template, then you can go into your code and make a nice parametric circuit out of this. And that's what's done here, where we have a finished circuit that started from a schematic. And the next thing we can do when we finish our circuit is we can validate our circuit and we can have a look at the connectivity. For that, we can use the method toCanvas. If we now run this, we will visualize our splitter tree. So this is our splitter tree that's made in a parametric way. And then we go back to Canvas and we can check if everything is well connected. And now you can see that there are these waveguides between these components. Well, that is because now we didn't use Connect Logical, but we used the Connect Manhattan or the Connect Band connector that creates actual waveguides. You can have a look in the properties of these waveguides, and you can see all the parameters of this waveguide connection, which band radius it has, and also the length can be found in here. So if you want to check, okay, I want both of these connections to have the same length, then you can do that. Have a look at their properties. This one is 54 micrometer. And this one is also 54. Then that's the thing that you can do with Canvas. Now imagine you forget to create a connection between components and you want to check your connectivity of your circuit. Then you will see here, first of all, in visualization, and secondly, in Canvas, that there's no connection. But you will also see that we create an error message that there are unconnected ports. These two ports are unconnected, so they should probably be connected. So this is a great way using the toCanvas methods to check the connectivity of your photonic circuit. So I finished the part about circuit layout. Now I will go back to the slides. And I will go to component layouts. So can everyone see the slide of component layout now? Just to make sure.
Yes.
Okay, great. So I've told you how to create a circuit, and for that so far we always used predefined components from a PDK. But it's also possible to create your own components in IPKIS. And we also provide a powerful and flexible framework to do this. And for that, we use P-cells. P-cell is actually a blueprint for creating a component in IPKIS. And a P-cell has 3 different views. It has a layout view, a circuit model view, and a netlist. And if you want to create a component, you create the class MMI the name of the component, and you inherit from P cell. And then you have all the functionality of a P cell for your component class. What you can then do is you can go into the layout class, and you can define the layout of your components. So in this case, we will create the MMIs that we've been using for the splitter tree. And we will start by creating the layouts, and that is always done in the generate elements method of the P cell. And here we just draw elements of our layouts. So our MMI consists of 4 elements. One is the rectangle, and the other 3 are some wedges. And every element also has a specific layer. Then afterwards, we can visualize the layout by instantiating it and visualize it. You can also export it to GDS. You can do different types of visualization. You can virtually fabricate it and have a look at the cross-section. Afterwards, you can also add ports to your components, and that's done in the generate ports method. And for that, every port, so here we choose the input and the 2 outputs. It has a name, a position, and also a trace template. And a trace template defines the actual cross-section of the port. So in the trace template, the layers are positioned, and together with the PDK, you can create a cross-section. You can virtually fabricate this cross-section. So inside the trace templates, you can find the layers, the width of each layer, and you can also find simulation data. So this trace template also shows when you want to connect your MMI, your component, with another component, which components you can connect it with, and where tapers should be generated, and so on. So we create all the ports. We've created all the elements, and now we can make it more parametric. For that, we can take out the layers out of the trace templates and the width as well. And then we can use all these components, use all these parameters in our elements methods. We can also define the width, the length, the spacing as different parameters, and create a fully parametric MMI. Then also you can go further. Instead of a 1x2, you can create an nxm MMI and add parameters for the inputs and the outputs. When you create such a component with that many parameters, it's always useful to add property validation to make sure that the component that you create is an actual physical component with an actual physical layout. What I mean with this is, for example, if you create an MMI with 10 inputs and only a very small width, then you will end up with an unphysical component that's not useful inside a photonic circuit. So that's why we create some property validation methods in which we have a look and see if we actually create an MMI with the parameters we've specified. And if that is not the case, so here we have a look at how many inputs and outputs and how high the width is. If the width is too low, then there will be a property validation error and you won't be able to create your MMI. Once we've created a fully an MMI that has nice simulation results, then we can lock the properties and we have a fixed cell. This is useful because you don't want, once you have a perfect design, you don't want to change any parameters anymore, also not by accident. So that's how you create components. Once you have a fixed cell, a component, you can add a component model to it that can be used in circuit simulations. So when you simulate your components, you can use either a device simulation, which is very accurate but very computationally intensive, or you can define a compact model for your components. And what a compact model does, it describes the components, or the transmission between ports in a component is described with a scatter matrix. And a scatter matrix relates all the input and output ports with transmission and reflection coefficients. And once you have the scatter matrix for your components, this scatter matrix can be used in circuit simulations, and you can do circuit simulation fast and accurate enough to have predictive value. So this is what I've explained here. We have components with a compact model. Then we will use CAFE or circuit simulator for either frequency or time domain simulations. And then we can have a look at the transmission between any of the two ports of the full circuit created with all these component models of your components used in this circuit. And this can either be wavelength or time-dependent simulations. So let's have a look. We have our MMI, we have our fixed cell of our MMI, and we want to create a compact model for our MMI. What we need for that is first we need some parameters, which is some information that gives us data to build our scatter matrix. And this information can come from anywhere. It can come from an external simulation. It can come from analytic equations or experiments and so on. Then once we've imported all this data, we define our inputs and outputs of our MMI. And then we define our scatter matrix in the calculate scatter matrix method. So here, the transmission between input 1 and output 1 is equal to the transmission data from our simulation, for example. Once we've built our full scatter matrix, we can add this compact model to the circuit model of our P-cell. Then there's also ways to make your models more data-driven. If you want to make a more light model, you can also always fit your raw data and then pass your fit to the model. In the end, we add a compact model inside circuit model view of our P-cell. And once we have components that have models, we can do circuit simulation. So here we will have a look at our splitter tree again, and we will simulate our full splitter tree because our MMIs, we've just created a compact model for it. And for that, we will create our splitter tree circuit, which we've created a layout already. And then we will take out the circuit model, and we can get the total scatter matrix of our inputs and outputs of our circuit. The next thing we can do is we can visualize these the transmission between the inputs and the outputs of the exposed ports of our circuit. So here it's visualized in this way. Then you can see that all the outputs have the same transmission, and there's a very low reflection here from input 1 to input. We can do frequency domain simulations. So here we have an example of a Mach-Zehnder interferometer, which is made parametric with the path difference over here. What is easy to do in IPCIS is we can sweep our path length difference because we've created a parametric component. And so in this case, we have a look at the transmission for 3 MZIs that are completely the same, except for the path difference. So we create a for loop in which we have created 3 different MZIs, where we take out the circuit model and we visualize the scatter matrix. And then we can see 3 different graphs created by the scatter matrix. So next to frequency domain simulations, we can also do time domain simulations. And for that, we use the virtual test bench circuits. So in the case of an MZI, what we do is, if we want to have a look at the time-dependent behavior, we specify a test bench where we add optical components, optical sources, and electrical sources. And then we have a look at the outputs, and we attach a probe to the outputs. And in this probe, we have a look at the time response that is created by simulating these optical sources and electrical sources in the time domain. So we define encodes. It just looks like this. We have a circuit. We use I3Connect components in which we define the child cells and the links between them. And then we have a look at the time response of this circuit, and we put it in this result variable. And then we can visualize it as follows. Okay. So, are there any questions about this part? About component simulation, circuit simulation, or layouts, and so on? Okay. Then I will continue with the slides. And have a look at our application example. So you can find this application example on Luceda Academy. And as I showed you before, this is the quantum key distribution receiver, where we have an input with a phase encoding, and at both of the outputs, it is decoded with help of this circuit. So what I'll go over in the slides, first I will talk about the working principle of the different components inside the circuit. Then I will talk about how we create the layouts, and then I will talk about how we create the time domain simulation with the test benches. So the most important part of this circuit is this asymmetric MZI, where we choose a time delay. And so what happens here, we have our input of pulses. And at this part, a pulse is split into 2 equal intensities. And one pulse goes through these spirals. And it is made, these spirals have a certain length, are tuned to a certain length, so that the first pulse comes together with the second pulse in this directional coupler. And then dependent on the phase difference between these pulses, it will come out of a different output of this directional coupler. So there are a few ways to tune this. We can choose one spiral or 2 spirals, or go up to 7 spirals. And we can also tune the stops phase shifter to make sure that that the 2 pulses come at the same time, which is very important, so that there's no interference and that no intensity can come at both outputs, that there's always one output with intensity. So this is then when you have the simulation results, you can see this is the input pulse train. These are all qubits with a different phase encoding, either 180 or 0. And you can see that when 2 pulses have the same phase, it will end up a blue output, and when 2 pulses have a different phase, it will end up with a red output. And this is output 1 that measures intensity, and this is output 2. And in this way, the quantum key is decoded from the encoded input pulse train. So that's about the working principle. Then there are some other components that are important for this circuit. And one here is the MZI for loss balancing. And in this MZI is created because we want to create a variable power splitting. Because if you go through spirals, there will be a higher loss in this arm than in this arm. So to make up for this loss difference, you create a loss balancing MZI with a different variable power splitting, depending on the loss propagation from the spirals. Sorry. So that's about the MZI for loss balancing. Then we have one more component, which is a tunable beam splitter, which can also split the beam to the bottom PDK, to the bottom output photodetector. And this is done in a different type of protocol, the COW protocol. But in our case, we will use a DPS protocol. So all the energy, all the light is routed to this upper arm. So that's about the working principle. What we've done in IPGIS is we've designed this full circuit by using components from our SciFab PDK, which is our PDK for silicon. And we use silicon nitride components to make sure that the loss is at a minimum. So we use silicon nitride waveguides, directional couplers, and heaters, all out of the SciFab PDK. And then on top of this PDK, we've created our own user library where we created components like the MZI and the spirals that can also be used in this circuit. So with these components, we created some circuits. First, we've created only the receiver. And then we've created a new circuit, which is the routed receivers. In our PDK have models. We are able to create a test bench which simulates the pulse propagation of a certain input bit rate at a certain optical power. We also select how many spirals we want the pulse to go through, dependent on the period of the bit rate of the input pulse train. Then there is a function bias receiver, in which we calculate the bias of all our MZIs, of all our shifters, and then we simulate the results. So let's have a look in PyCharm. So if you have a look in training, topical training, then you can find quantum key distribution over here. And here you can find the example of the quantum key distribution receiver. So we have a few files here. This is in receiver.py. We've created the receiver class or circuits. In the same way, we always create a circuit. We define the instances and the specs. And then we also create a routed receiver in which we define all the electrical connections with the bond paths and also the optical connections to the couplers, the I/O. And in this test and tune benches, you can find all the test benches that are created to simulate this design. So these functions, here we create an optical pulse train, we create signals for our inputs. And then we have our bias function, which calculates all the bias of the MZIs dependent on the optical inputs, on the power and the bit rates of our input pulse train. And this is inside so these two files are inside the quantum key distribution receiver folder. And then we have two separate codes files in which we actually instantiate our receiver over here in example receiver, where we've created a receiver and a routed receiver. And we have another file where we actually simulate the receiver that we've created. So if you run the simulate receiver file, let's have a look what's in this file. So first we have the input statements, the import statements. Then here you see the information about the inputs, the pulse train. So the power, the central wavelength, then the bit rate. We see it's 581 picoseconds is the period between two pulses. And for that we choose two delays, which are two spirals. And then we can also say specify the optical noise of the signal. So once we have our inputs, we can use our bias receiver function that calculates for our inputs all the biases, voltages of the MZIs. And then once we have this, we can actually simulate our receiver in which we input our receiver and our voltages and also our bit rates. So if we then run this, then we can also follow here. So this is one of our shifters. The first thing it does is it's calculated the voltage for maximal coupling. You see here the voltage needed for every MZI switch. Then we calculate the voltage for the loss balancing. Then for the tunable beam splitter. And for the TOPS shifter. And once we have all our bias voltages, we are able to run our complete test bench and have a look at the output response of our two outputs at the directional coupler. So here we can see the inputs again with the encoding, and then the outputs of the two outputs of the directional coupler at the end of the circuit, which are then attached to photodetectors. So this is a way how we create and fully simulate photonic circuits in IPCIS. Are there any questions about this application example? Oh, I see. Can you please share that PY file for simulate receiver so that we can try it later?
No, sir.
No.
Okay, no more further questions. I can see in the chat the .py file for the simulate receiver. So all of these, I just want to add that everyone in this training has received an IPCIS license that you can still use until the end of next week, I think, until 7 more days. And you can find all of these application examples inside Luceda Academy. So if you open Luceda Control Center, and then you come to this menu, and you can click right here, open Luceda Academy project. And then you get in this project, Luceda Academy. And you can find training material, the getting started material is all explained in the Luceda Academy as well on our online platform. And here in the topical training, you can find the quantum key distribution example. So everyone has access to these files. So we've come to the end of our session. Are there any more questions?
Yeah, any participant have any question, please?
Hi. Suppose if you want to design an active device, how do we do that? Can I include doping there?
Yeah, any participant have any question, please?
So you're talking about an active component. So we have we can create active components if they have a certain model. So, for example, an MZI. Do you consider an MZI as an active component, or what is your definition of an active component? Or how do you see an active component?
Could you clarify once again? Sorry, I didn't get it.
Okay. So you are asking if we can also create and simulate active components. I think with active components, you mean, for example, electro-optical components, like an MZI with a certain heater. And that's definitely possible. We have models for this. We can also route electrical connections. So it is definitely possible. Is that clear, or is it something else that you mean?
Yes.
Okay, great. Any more questions?
No, clear. Thank you.
Okay. Okay, thank you very much. If there are no more questions, I think we can end the session. Thank you very much.
Thank you. Thank you, Turun. It was a great session. We are thankful to you for sparing your time.
Okay. Thank you very much. If there are any more questions, or I can see. Oh, I can see there's another question coming up there. Please share one more time how to open the library. Okay. So what you do is you, when you install the software, you can go to Luceda Control Center, which I will just do now with Windows here. And I can press here, open the Luceda Academy project in PyCharm. And then I will go directly into the Luceda Academy project inside PyCharm. And if you go then here into the training folder, you can find all the getting started trainings. And in topical training, you can find more advanced training subjects with also, for example, the quantum key distribution receiver. Does that answer the question about the library, or is it something else that you mean? Okay.
Yes.
Great. Okay. If there are not any more questions, I would like to thank you for inviting Luceda to join this this course. And you can now, for the next week, you can use the software and try out our examples. If you have any questions, you can always contact us on the support channel or send an email to us. We are happy to help you further.
Yeah,
thank you.
On behalf of VNIT, we express our heartful thank you to you for delivering such a wonderful session. Thank you.
Okay, thank you very much. Goodbye.